Günaydın. Hoş geldiniz. İsmim Berat Haznedaroğlu. Boğaziçi Üniversitesi Çevre Bilimleri Enstitüsü'nde yardımcı doçent olarak görev yapıyorum. Jonathan'ı birazdan podyuma davet etmeden önce çok kısa bir iki kelime Boğaziçi Lectures serisi hakkında bahsedeyim. Bir de biyografisinin çok az bir kısmını Türkçe söyleyeceğim. Ondan sonra İngilizce olarak devam edeceğiz. Boğaziçi Lectures Series bizim 2013 yılında üniversitenin 150. yılı kutlama aktiviteleri çerçevesinde başlattığımız bir konuşma serisi. Bu konuşma serisinin amacı dünya çapında kendi alanlarında uzman akademisyenleri, bilim insanları, topluluk liderlerini üniversitemize davet ederek kendi alanlarındaki araştırmalarını üniversitenin akademik ortamında kamuoyuyla tanıştırmak, araştırma alanlarını tartışmak. Bu sene de Profesör Doktor JonathanTrent bu serinin 10. konuşmacısı. Çok kısa biraz kendisinden bahsedeyim. Dr. Trent, Omega küresel girişiminin kurucusu. Çok fazla detay vermeyeceğim, kendisi zaten anlatacak. Onun dışında NASA'nın Ames Research Merkezi'nde Astrobiyoloji programının başında. Aynı zamanda Kaliforniya Üniversitesi'nin Santa Cruz kampüsünde de yarı zamanlı olarak ders veriyor. Kendisinin uzmanlık alanı sürdürülebilirlik, deniz mikrobiyolojisi, astrobiyoloji ve nanoteknoloji. Doktorası Scripps Institution'dan, Kaliforniya'da, San Diego'da. Onun dışında Almanya'da Max Planck Institute for Biochemistry'de araştırmalarını yaptı. Kopenhag Üniversitesi, Paris Üniversitesi ve Yale Tıp Fakültesi'ndeki Boyer Moleküler Tıp Merkezi'nde de araştırmalarını yaptı. Jonathan aynı zamanda da Kaliforniya Bilim Akademisi'nin de yaşam boyu üyesi. Şimdi çok kısa da İngilizce biyografisini okuyayım. Ondan sonra da çok fazla vaktinizi almadan konuşmaya devam edelim. So it's my great privilege and honor to introduce you Professor Dr. JonathanTrent. He got his Ph.D. From Scripps Institution of Oceanography at San Diego. He is holding an adjunct faculty position at UC Santa Cruz, and he's also the head of the Astrobiology Group at NASA Ames Research Center. He's the founder and the director of Omega Global Initiative, which he will talk a lot. Some portion of this talk is going to be on Omega. He did research at Max Planck Institute for Biochemistry, Copenhagen University, University of Paris, Boyer Center for Molecular Medicine at Yale Medical School, Argonne National Lab, and Jonathan is also a lifelong fellow of the California Academy of Sciences. Jonathan, the floor is yours.
Well, it's a great honor to be here, and I'm looking forward to finding out what you think about the presentation I'm about to give you. And I'm particularly honored to have high school students in our midst. And the reason, as you'll see from my presentation, is because we're at a very special place in the history of our species. And what I want to talk to you about today starts with the question of the world, will include issues with regard to Mars, and finally I'm going to talk to you about the Omega Project. So let us begin, because this, unlike a typical lecture, is really meant to be somewhat of a journey through our history. But before we start, you know, I've come here now from Silicon Valley. And in Silicon Valley, people are very much focused on startups. And there are 5 elements to a successful startup. And they have to do with these 5 things. First, there's the idea. Then there's the team. Then there's the business model, the funding, and the timing. So if I were to ask you this question, what is the most important of those 5? How many people in this room would say the most important thing is the ideas? Raise your hand. Okay, good. The second thing is team. How many people think the most important thing in a startup is the team of people? Raise your hand. Okay. The third is the business model. What about the business model? Raise your hands. Oh, not too many people think the business model is important. What about funding? Okay, good. Funding is important. And what about timing? How many people think timing is important? Ah, interesting. Okay. Well, there's a very famous Silicon Valley entrepreneur who's been working in this area for a very long time, Bill Gross, and he gave a TED talk about this. And these are the results. The most important thing is timing. The most important thing, and about a third of you said that's the case, the least important thing was the funding. The most important thing for making a successful startup was doing at the right time. So part of the reason I wanted to start my presentation is because during the rest of this talk, I want you to think about this issue of timing. Because society now is at a very important transition. We're at a transition now in which we've been in this old model in which linear systems where natural products are transformed into products and wastes. And we're about to see a transition in which circular systems where products are being formed from natural resources and wastes are becoming resources to make these types of circular systems. Now, one of these types of circular systems is the Omega Project. And the Omega Project is a project that initially started with studying algae, and we built a systems that would be floating offshore called operational marinas for economic growth and abundance. But if we can have the lights down, I would like to start my presentation now by talking to you about a very broad perspective. And I'm going to give you a global perspective, the perspective in which we look at the Earth as a system. We look at the whole history of the planet and our place within that history. And what we'll see if we look at our species, the most critical elements of our existence as a species on this planet have been really three elements. Those three elements are energy, food, and water. Those three elements have defined our civilization from the earliest time. And those three elements are going to be critical in the future, as they still are now. But first we have to put this into the context of our planetary system. And in this picture taken from space of the Earth, you see this very, very faint and very thin blue veneer around the planet. That thin blue structure is the atmosphere of our planet. And that atmosphere, if we look at it for the last 650,000 years, that atmosphere has been changing. The amount of CO2 in the atmosphere has been going up and down and up and down. In fact, if we plot the amount of atmospheric CO2 in parts per million, it's gone up and down and up and down and up and down for the last 650,000 years, up until the time of the Industrial Revolution, about 250 years ago. Now, if we put onto the same plot the times where the glaciation on the planet, the ice ages changed. An ice age ends everywhere the CO2 goes up. Ice ages end when the CO2 goes up. If you look where we are right now, the CO2 is here. For the first time in almost 1 million years, the CO2 levels are now above 300 parts per million. They're over 400 parts per million on average. So this is something we all know about. I mean, in some parts of the world, it's still disputed whether or not the science is real or whether it's a political decision. Even where I'm coming from, it's now become a political issue. But the science is actually quite clear. The CO2 levels in the atmosphere have been going up and down and up and down, and the ice has been retreating and advancing and retreating and advancing. Now, in this timeline of 650,000 years, Homo sapiens like us fit here. Our species, Homo sapiens sapien, is about 200,000 years old. 200,000 years is how long we as a species have been identified on this planet. So, We can look at a longer time frame, and in fact, let's look at my family tree going back 2 million years. So here's the family tree. These are the species there. This is my relative of a Neanderthal that might be about 200,000 years. The Neanderthals died out. They overlapped with our species somewhat. But this goes back about 2 million years, the species shown here. So what's critical about our species? What's critical about the last 200,000 years? The critical thing is that we have gone from being hunters and gatherers to becoming farmers, to becoming industrialists, and now becoming computer geeks. Well, in fact, now we carry our computers in our pocket. And you may not realize this, but the computer you have in your pocket is about 3,600 times more powerful than the computers that NASA used to go to the moon in Apollo. So your little handheld computer, that is your iPhone or your equivalent to an iPhone, that you're carrying around with you is thousands of times more powerful than any computer used to go to the moon. What's interesting about this transition we've seen in our species is the time that we've spent in each of these categories. In fact, of the 200,000 years, 188,000 years we were hunting and gathering. About 10,000 years we've been doing farming. Only about 250 years have we been industrialists, and less than 70 years have we been doing computers, even though now we take computers completely for granted. What does this mean? This means that 93.9% of our history, we have been hunters and gatherers. 6% of our time we've been doing farming, and now we're up to 99.9% of our history is farming and hunting and gathering. 0.1% of our time we've been industrialists, and 0.025% of the time we've been using computers. 93.9% of the time that we've been a species, we've been living like this. We've been asking some very simple questions. Can I eat it? Will it eat me? But most importantly, we lived in small groups of people and we moved around. The small band of our relatives, our aunts and uncles, our friends, we moved from place to place. And there were so few people that we would stay in one place as long as the animals were there, and most importantly, as long as there was clean water and we could find some source of energy to keep warm. So this is particularly interesting here, right? Because we're here at the Fertile Crescent. We're here at a very historically important place in the history of our species. But clean water, energy, was most of what we were looking for. In fact, our whole history has been about food, water, and energy. This is who we are. As hunters and gatherers, it was about finding food and keeping clean water. And we would stay in a place long enough, and only so long as the water was clean. As soon as the water became dirty, we would have to move on. Once we became farmers, we changed very significantly, which happened really close by to here, as far as we can tell, as we left Africa and came into the Fertile Crescent, where the Tigris and the Euphrates made these incredibly rich areas. We started farming and staying in one place. Industrial world was about the food, water, and energy system, and now that we have excess of all three of these, we're allowed to be computer geeks. You know, in Maslow's pyramid, it's only now that we're really getting to the top of that pyramid. But let's put this in perspective. Here we are 200,000 years ago following the carbon curve, and it's not until here that we become farmers. After the end of the glaciation that ended about 12,000 years ago, we start farming right in your backyard, right south of here. We become industrialists on this curve here, and we're doing computer geeks in not a measurable space. Think about this. Since the last glaciation, ignoring all the previous history, but just since here, the glaciation ends here. 10,000 years ago, we find good evidence of agriculture. And you know that China and Mesopotamia and Egypt, these are all ancient civilizations that we can trace back already 6, 7, even 8,000 years before now. Anatolia and the Greeks are about 3,000 years old. Persia and Rome about 2,000, 2,500 years old. Constantinople, 2,000 years. The Vikings, 1,000 years. What does this mean? This is the timeline since the end of the last glaciation, relative to the 650,000 years of carbon up and down. It's a pretty short time, but for us, it's a really long time. Let's look at what's happened to the population in the world since the Vikings. Each dot on this graph represents 1 million people, and we're counting up from the time of the Vikings. At the time of the Crusades, look at the people distributed in the world. China and India, abundant. The Mongols come and dots disappear as the Mongol horde kills millions of people. The Black Plague in the 14th century kills half of all the people in Western Europe, and the dots are disappearing. And the Europeans set out and bump into North and South America, and look at India and China when the quote-unquote New World was being discovered, and the Incas are being destroyed by imported diseases from Europe. And look what's going on in Europe, in Europe compared to India and China. Look at the distribution of people in the world at the beginning of the Industrial Revolution, 1820. China, India, Japan, Europe. Look at North and South America, relatively speaking. If we do a plot of this, we realize by the time we get to the Industrial Revolution, China and India in red, Europe in blue, Africa in green, the Americas in black. China, India totally dominate the world's population. Over 50% of the world's population is in China and India. Europe in blue is representing about 10 or 15%, fairly stable through this whole period of time. Africa representing 10 or 15%, pretty stable but going down a little bit at the beginning of the 19th century. And the Americas, pretty sparsely populated. At this time, the world's population reaches 1 billion. And the population is now growing at an incredible rate. You guys, the students, show up around here, and the population now is 7.4 billion people. This has never, ever in the history of our planet been the situation where there are so many people. Where are we now? 2017, China and India are still dominating the world's population. 51% of the world's population live within what's called the Asian Circle. If we follow what's happened in the since the industrial age, the world wars, a few million people, but look at all the people in the world as we push out into the future. The question for you is, here is the most abundantly populated part of the world. And within this circle is 1/4 of the inhabitable space on Earth. And yet, if you look in the red dots indicating the numbers of people in the various parts of the world, this is where all the people are. Look, here we are in Istanbul, a tiny red dot there compared to the rest of Turkey. Look at Europe. You can see London, there's Paris. You can see population centers. Look at the United States. The United States is 4.4% of the world's population. Hardly anybody living there. Third most populated part of the world is the United States. But only 329 million people, compared to India, which is 1.3 billion people, and China, which is 1.4 billion people. But aren't you wondering why? Why, since the time of the Vikings, even before the Vikings, have there been so many people inside that space? Why? What is the reason that there's so many people living in that place? So I bet you know the answer, and it's on the tip of your tongue. The answer is the Tibetan Plateau, the Himalayas. The Tibetan Plateau is the third largest supply of fresh water on the planet. The first is Antarctica, the second is a Greenland ice sheet, and the third is the Tibetan Plateau. Why is the Tibetan Plateau so important? Fresh water. The Indus River, the Indus Valley, the Ganga, the Ganges, the whole of the Mekong Delta, the Yangtze River, the Yellow River, the runoff is providing not only fresh water, but rich soil. It's food, it's water, and it's energy. This region has been so heavily populated because of the supply of clean water. So how many people have seen Leonardo DiCaprio's film with National Geographic? Oh, only a few of you. I showed you this because it's about the whole question of climate change that was presented by the National Geographic, and Leonardo DiCaprio was the lead on this. The real reason I showed you this is because the data are telling us that the real consequences of climate change in terms of the impact on our whole planet is that the Tibetan glaciers are melting. The Tibetan Plateau will disappear in anywhere from 50 to 100 to maybe 300 years. So for our lifetimes, that may not be significant, but for the overall distribution of people on the planet, given what I just taught you, it's very, very significant. What this means is that this type of immigration that we're now seeing out of Syria and obviously impacted your country enormously is a tip of the iceberg in terms of climate's impact on the human species. Because what's going to happen during the lifetime of the students in this room from high school is that the population, when you are my age, will be somewhere around 9 billion people. The population on the planet is continuing to grow. Now, there's a cartoon that says, now for religious and political reasons, let's pretend that none of these are related to overpopulation, the energy crisis, the food crisis, the water crisis, and the environmental crisis. Welcome to conventional wisdom. This is not the whole story. The reality is, when we look at our planet globally, the population is part of the problem. But urbanization is another part of the problem. Urbanization, the movement of people from farms to cities, the incredible rapid growth of cities. Consider Istanbul, but consider China. Only 20 years ago, less than 30% of the Chinese population lived in cities. Now the number's over 50%. In the United States, over 80% of the people are living in cities. Urbanization is a huge part of what's going on. Affluence, our expectations for lifestyle are changing. Our ability to eat meat is changing. And the climate change itself is making a perfect storm. Population, the urbanization, the affluence, and climate change are influencing the food, the water, energy, food nexus. This is significant. This is going to happen within your lifetime. Partially within my lifetime and the lifetimes of most of the people in this room, we're going to see changes. Now, one of the worst things that I think anybody ever does in the name of climate change is they present the kind of presentation that I just presented to you, in which we're all thinking, wow, this is scary, but there is nothing that we can do about it. And this creates a level of frustration that is not very helpful. So I want you to consider possible solutions with me. So the rest of my presentation is going to focus on solutions. And let's start out on one of the more radical solutions that people have been talking about. And that solution has to do with, let's leave. Let's go to another planet. I mean, there are people in the world now seriously considering, maybe we have outgrown the Earth. Maybe we need to set up a place to live beyond the Earth. and maybe we should go to Mars. Now, I know you're probably thinking this guy's nutty, right? But there's a lot of people who think that Mars could be a destination for our species. So because I'm from NASA, although I'm not representing NASA, in fact, NASA would probably not be happy about what I'm about to tell you, but I want to talk to you about Mars because NASA is planning trips to Mars. NASA already has an expedition on Mars, and there's the rover there called Curiosity, and Curiosity is rolling across the surface of Mars and sending back fantastic data. In fact, we have pictures of our own tracks on the surface of Mars. And Mars is really being seriously considered as a potential site for human colonization. So let's go to Mars.
9, 8, 7, 6, 5, 4, 3, 2, 1, and lift off.
Okay, so we're on our way. First, we're going to have to scan the launch. And we'll be getting about 5 to 7 Gs, pretty tough, but we can cope with that. We're then going to be underway for about 8.5 months. We'll be sitting like in economy class. It won't be very comfortable. And we'll be exposed to a lot of radiation. We actually don't know how to get you there without damaging your eyes or your brains, but we'll figure that out in the meantime. Next, we have to land. We have to slow down from about 7 kilometers per second to 0. We have what's called the atmospheric brake. That slows us down to about 1,600 kilometers per hour. And these are actual images of the Curiosity lander. That's the heat shield falling off the Curiosity lander, and that's what Mars looks like as Curiosity came down to the surface. These are sand dunes. That's what Mars looks like at the surface. Notice, in order to actually land, we're going to have to use some kind of retro rocket because we have to slow down to 0 by the time we get to the surface. This is one of the most dangerous aspects of what's going to happen. So this is the camera from the Curiosity lander, and that's what Mars looks like really close up. So now we're on the surface of Mars with the Curiosity rover. We're going to be landing in what's called the Mars Landing Device, and we're going to look out over the sand and dust and rocks, and it's cold outside. The average temperature outside is minus 60 degrees. The warmest day is 20 degrees, and the coldest day is about minus 120 degrees. Now we're going to have already some things there because we're going to need pressurized rovers to move around. Because the atmosphere is not only not breathable, that is, it's mostly CO2 and less than 0.2% oxygen, but the atmospheric pressure is so low that water on Mars boils at 4 degrees. Your body temperature is 37 degrees. That means if you're exposed to the Martian atmosphere, all of the liquid in your body would boil. You would freeze to death, but your body would boil. At night, the temperature is about minus 75, minus 85 degrees. To live on Mars, we're going to have pressurized chambers already in place, and they're going to have to grow food for us because this is going to be breakfast, lunch, and dinner. We can only carry about 62 days worth of food, so we're going to have pre-growing food for us to survive. The chamber that we're living in has to not only be warm and pressurized, but it has to be modular, because if anything goes wrong, we're going to have to fix it in place. Everything for maintaining our spacecraft, our home away from home, is going to depend primarily on what's called long-duration life support systems to maintain temperature, provide oxygen for us to breathe, and pressure, these long-duration life support. It's like living in a submarine. Now, we can go outside, but going outside, given how cold it is and the radiation levels, we're going to have to wear some pretty warm underwear, and we're going to have pressurized suits. The dust on Mars, we now know, is toxic. So if we bring the dust back inside, we have to be really careful. these sort of base suits that we're going to wear to allow us to go outside will let us enter an enter the environment that has dust and rocks and dust and nothing else alive. In fact, the radiation at the surface of Mars is so strong that there will be nothing living at the surface of Mars. Now, you probably know that Elon Musk in his SpaceX is planning to bring 100 people to Mars in the 2020s. So how many people would go to Mars if Elon offered you a ride? Raise your hands. Oh, not too many people are volunteering. Oh, good, we have two volunteers. Well, Elon is going to go with you. It's a pretty tough place to live. When asked, why would you ever want to live on Mars? Elon's response was, it looks like a great adventure to me. An adventure it would certainly be. How many people here saw the movie Martian? Raise your hands. Oh, good. How many people didn't see that movie? Okay, so only a few of you didn't see the movie. The movie is kind of cool. It's about an expedition to Mars, and they have this dust storm, and this one guy, who's Matt Damon, is left behind. They have to leave because their spacecraft is blowing over, so they have to leave in a hurry. And he gets left behind. And he survives. I mean, that's a little bit of science fiction, the way he does that, but it's cool. And the movie then is about finding a way out.
The greatest botanist on this planet.
So this movie is interesting from the standpoint that he had to science the shit out of this in order to survive. It actually wasn't a movie about Mars. It was a movie about our ingenuity. It was a celebration of our ingenuity. And we know from the rovers that are wandering on the surface of Mars right now what the conditions are like there. I told you about some of the things that we've learned about Mars from the rovers that are physically there right now. Now, a rover doesn't mind that the temperature during the day may be 20 degrees, and the temperature that same night will go down to minus 85 degrees, 100-degree temperature change from a day to a night to a day to a night. The rover doesn't care, and the rover's providing us with wonderful data. So the question is whether or not the reason we're going to Mars is because it's an incredible adventure and a celebration of our pioneering spirit, or as Elon says, it's a way of setting out outposts so that our species will survive if things go wrong. I think our thinking about Mars is the same reason that we celebrate the ingenuity of our primitive our ancestors, who used tools and makeshift weapons and things to chase animals away from the kill to be able to get food. And Mars is an interesting thought experiment because Mars has so few resources that the waste products from the humans living on Mars will become the greatest source for food, energy, and water. Mars itself provides a little bit of solar energy, no really useful water, because the water on Mars is contaminated with salts. And if it isn't contaminated, it will boil already at 4 degrees, which means it goes from a solid state to a gas state. So Mars provides little energy and little water and no food. But thinking about putting people on Mars forces us to think about the most incredible recycling system you can imagine, because the waste products are so valuable. Mars is an object lesson in water, energy, food systems, where the systems are systems of systems. And I submit to you that this idea of thinking about putting people in space provides us with a very valuable tool for thinking about how the Earth, as a food, water, energy system, can be optimally utilized. That is to say, we can think about the energy, food, water, and the environment in terms of developing a green economy.
The project is called Omega. It's for coastal cities. Let me tell you how it works. Omega uses protected bays, like San Francisco Bay. Vast areas which will get even bigger with sea level rise. And most importantly, they already have wastewater treatment plants that currently dump wastewater into the bays. But for Omega, this wastewater is a resource, redirected into floating clear plastic tubes to grow microalgae, the fastest growing plants on the planet and the best producers of oil. The algae grow using nutrients in wastewater, and they use concentrated CO2 from a source like flue gas, which means Omega treats wastewater and captures and controls a major greenhouse gas. The Omega infrastructure is used for solar electricity and concentrated solar thermal. And in some locations, wave-powered generators and wind turbines will also provide power. In addition to energy, the Omega offshore platform supports aquaculture and produces high-quality food without using land and without using water. In fact, saving water is a big deal. It's estimated that by the year 2030, half of all the people in the world will face water shortages. And the current map of water scarcity shows in red that there are already many places in desperate need of clean water. Adapting methods developed for the space station for recycling water, Omega transforms wastewater into clean water using 1/3 the energy required to make clean water from seawater. Omega improves the environment by treating wastewater and capturing CO2. It increases the availability of clean drinking water by recycling wastewater. Supplies food without competing with agriculture. And it provides solar energy as electricity, heat, and biofuels. All things that help move us toward a green economy and a sustainable society.
So this is just one example of our potential ingenuity in dealing with this closed system. The Omega project started as a NASA project and now is initiated as a nonprofit called the Omega Global Initiative, OGI. So what are we trying to do? What we're trying to do is show that we can integrate the growth of microalgae, the fastest growing microbes on the planet, the cleaning of wastewater into drinking water, the farming of the oceans, and utilization of solar energy for electricity and heat, taking advantage of an offshore environment. That is, using a space that is currently underutilized. So if we think about this, we already have infrastructure offshore that allows us to reasonably think how this could work. We know how to do aquaculture. We've been doing aquaculture for nearly 4,000 years. Algae cultivation, I mean, you already know how to do algae cultivation in your institute and others as well. And solar energy in an offshore environment is already being utilized. Wastewater purification is known. The real question is, can we bring all of these together and can we put them on an offshore floating platform in some place where the water is sufficiently calm that we could build and design at least the first prototypes? And can we build it so the interaction of all of these things becomes synergistic, so that we build an ecosystem, so that the offshore infrastructure helps us do solar energy, and the solar energy helps us do aquaculture and algae cultivation, and all of this helps us do water purification. The practicality of this is within reach. We know how to do algae growth, but in order to do biofuels, we have to do a really large scale. We know how we can use algae to capture carbon, which would help us in the greenhouse gas problems. We know how to reuse wastewater as a drinking water at a fraction of the cost of purifying seawater, that is, making seawater into drinking water. We can do solar electricity with a much higher efficiency than ever before, and we can capture concentrated solar heat, and of course we can do aquaculture. All of this could contribute to the water, food, energy resources that we need. So what's stopping us from building the Omega system? I got $10.8 million in 2010 to do a feasibility study of the Omega system, and by 2013 we had realized that it's not possible to do algae alone, but that we could build the integrated system. After 2013, and NASA funding ended, and in 2015 I started the Omega Global Initiative, and I've been going around the world to try to find places where we could build the first exemplars of the Omega system. There are three things that we need to get past in order to do the Omega system. The first one is location. The second one is location, and the third one is location. But I'm serious. The three critical factors are the location, location, location, where the first location is the physical location. Is it too cold there? Is the water temperature okay? Are there typhoons? What about the weather in the rest of the year? The second location has to do with the engineering. What are the logistics of bringing the wastewater or the CO2? What are the logistics of building offshore? The third location is actually the most formidable. What is the social attitude? What is the social context? What do people think about building something like this in their offshore environment? These three locations are major hurdles. The physical conditions, we can find places that are adequate. The engineering is well within our capabilities. We can send people, we can send robots to Mars. The social engineering is more formidable. We have recently submitted a grant proposal to the Belmont Forum in which we call Sustainable Urban Global Initiative, SUGI, which is a food, water, energy nexus proposal. And part of the reason I'm here is because the four partners include Berat's lab and here in Turkey, a group in UK, a group in Taiwan, and my group in the USA. We're going to work on all three of those location issues, but we're going to focus a lot on that social component. Try to understand, what are the restricting features? How do we get around convincing people that this is a really good idea? But I want to introduce you to another project. I call it the Economic Farm Project. Eco because it's ecological, nomic because it's a law, the environmental laws that we're going to try to deal with on a farm basis. And what it's going to focus on is a systems approach to industrial agriculture and fertilization. The biggest sources of greenhouse gases are about 15% transportation, and a huge component is industrial agriculture. I seriously want you to think about this part of the project, because this is an interesting idea that's related to the Omega project, but maybe easier to implement. And it has to do with the idea of using our farm animals, the beef, the lamb, the chickens. And we know, for example, that in a dairy farm we can produce milk and meat, but we also produce huge amounts of manure. Now, in countries where they're very careful with the manure, they use the manure in anaerobic digesters to make methane or biogas, and they can also make fertilizer. Both of these are producing greenhouse gases, which is somewhat of a problem. The manure is then used as a fertilizer to grow crops, and the crops feed our animals, and the animals and the crops feed us. But imagine that we take another approach to this. What if we design a system in which the manure is captured and a pond is built so that the water provides a liquid for transforming the manure into a liquid slurry? That liquid slurry becomes an extract that's used for growing algae in floating photobioreactors in a pond that we build or that we utilize on the farm. The algae in the photobioreactors are growing on the nutrients in the liquid manure, and the solid phase, or the sludge, goes into an anaerobic digester. The anaerobic digester makes nutrient-rich water that also feeds the algae, and it makes biogas. The biogas is burned to produce CO2, and that CO2 feeds our algae. The biogas is used to make electricity and heat for pumps and heat exchangers, and that heat can be used to pasteurize the manure, the liquid, and the solid sludge. The algae become a feed supplement for our animals, providing omega-3 fatty acid, proteins, and lipid and carbohydrate. And they can become a feed for a tilapia or some other herbivorous aquaculture species growing in our pond. The oxygenated water from the algae also contributes to our aquaculture, and the waste from the aquaculture becomes part of our anaerobic digester. If we need more energy, we can put solar panels or wind turbines on our farm. What did I just describe to you? The old system, which took the manure and turned it into biogas and fertilizer, had a problem with CO2 and grew slow-growing plants that fed our animals and provided food for us. The new system provides algae as an intermediary that feeds our animals, but also grows tilapia or some other kind of herbivorous fish that also allows us to still make fertilizer to grow our slow-growing plants, which feed our animals and feed us. We've added the fastest-growing plant on the planet, the algae, to our system, which allows us to add another layer of complexity to our farming activities and make more money from manure. The concept that we're talking about here has to do with this complex system, but basically taking the components of what our farm animals are producing as a byproduct and building it into a system that produces energy, water, food as products and services. This is essentially a closed-loop system like we used in our omega system, where we're having operational marinas for economic growth and abundance, and looking at how we can close loops, how we can build ecosystems. So let me recapitulate where we've been. We talked about where we began as our species within this timeline of CO2 and changes in our atmosphere, where farming starts here, industrialists here, and computers here. We acknowledge that our brains and that our whole societies have evolved from being hunters and gatherers, that we as a species, our brains are prepared to live in small groups and to hunt and gather. This is kind of who we are. That's what our brains evolved for 93.9% of our history, and the additional 6% to 99.9% was for farming. We find ourselves in a really difficult situation. Our ability to utilize fossil energy has put us in a huge population never before existing on the planet. We've moved to cities, which we're very happy for, and we're improving the lifestyle of affluence of many, many people on the planet. The price we're paying for all of what's going on the planet is now that we're so many, we're influencing the climate itself. This is going to impact the water, energy, food nexus. It's influencing how much water and food are going to be available for everybody. During the course of what I just told you, we considered the possibility that Mars would be an option, and I hope I convinced you that this is not really in life. That Mars was never going to be a place we're going to colonize. We may visit Mars, we may consider it a wonderful adventure, but we're never going to form a major colony on Mars. If you consider the Earth as a planetary system, life arose on the planet 3.5 billion years ago. all of the radiation of the Cambrian and all of the diversity of plants and animals that we see on the planet now that are macroscopic, that are large organisms, are tiny fraction of the overall history of the planet, about 580 million years during the Cambrian period. And we as a species have arrived only in the last fraction of a time interval, only 200,000 years. Even as an extended species of 2 million years, it's a tiny fraction of the 4.5 billion years of Earth history. Mars represents an exercise in understanding how to build a closed-loop system, but it is not someplace we really want to send people. We can think about Mars, and we, most importantly, should think about what it means for our own concepts of ourselves as not only a species that survives, but a species that is incredibly ingenious in our ability to survive. The Martian movie was a movie about celebrating our ingenuity, the ingenuity of Matt Damon figuring out how to survive on Mars. But that ingenuity was already manifested in our species way back when we were living as animals. It's always been this way. So when we think about our system, when we think about the system as a planetary system, we think about our place on the planet. We think about what it means for our species now to be at 7.4 billion, and that during your lifetime, especially your lifetime as younger people, you're going to see another major extinction, a change in the biodiversity on the planet. We're changing the structure of the planet itself. People are describing the period of history we're in right now as the Anthropocene, the period of time in the Earth's history when we as people are influencing the planet itself. For us, we have to learn to live with the planet to maintain the Earth, the energy, food, water nexus, and that we can then cope with these threats from this incredible, perfect storm of possible problems. I presented to you two thought experiments: the Omega Project as a floating infrastructure, and the Economic Farm Project as a way of thinking about closed systems. What I meant for you to think about is how we should think about going from a natural resource linear system to products and wastes, where the wastes are thrown away. I submit to you that away has gone away. There is no away anymore. We can't throw things away. So what we need to think about is how waste can become resources again and build circular closed systems. The real question that I started my presentation with, in order for us to be successful, we have to be doing this at the right time. So Einstein taught us that time and space are not different. And so maybe it's true that timing is everything in terms of the success of startup companies, but timing is also space dependent. And maybe here in Turkey, we're in the right space as well as the right time for us to start thinking in terms of building closed loop systems, both on the many, many farms that you have. There's millions of dairy farms, and small and large dairy farms, and chicken farms. There are many opportunities both in farming and in terms of the availability of coastlines that might be applicable to having coastal cities. And so even in Istanbul, we might be thinking of these possible Omega solutions. So finally, I'll end with a review of the idea that we've looked at the world from both a time and spatial perspective, looking at the very history of our species. We've considered Mars, and I've introduced perhaps some of you to the Omega concept. And I think there's maybe some time for questions.
the food, water, and energy nexus is as old as human history, and now it's more important than ever.
I think so too. Are there any questions?
Yeah.
You have argued that colonizing other planets is not a good idea, and the great science fiction author Isaac Asimov agrees, labeling this idea as planetary chauvinism. And that other than what you said, the planet imposes other constraints, such as surface gravity, the length of time, the severity of the seasons, and also you live basically at the bottom of a potential well. If you are, if you are thinking about transportation, etc., you are living at the bottom of a potential well. But there are those who argue that planet is not the only option of getting away from Earth, and we should have the option of going away from Earth, and you will recognize the name certainly, the building space habitats a la O'Neill. So what you have done, what you are proposing is the, how to reasonably utilize the resource, the planet that we do have. But what do you think about creating other options too? And as I said, habitats a la O'Neill.
So Elon Musk has said that go to Mars will cost $300 billion, and that will be cheap compared to what NASA would charge us to go to Mars. The question I submit to you is, can you think of anything better we could do with $300 billion than spend it on trying to figure out to go to Mars? Maybe not. Colonizing space is really problematic. I hope I presented to you that the threats. Look, I worked for NASA for 19 years. For many of those years, I was next door to a physiologist who studied the physiological impact of space exposure on human body. People, because we have watched Star Trek our whole lives, we have no idea how bad it is to put the human body in a weightless environment. There is no comparable environment on Earth where you're weightless. You can create an artificial gravity if that's what you're thinking by doing that, yes. But the reality of putting ourselves in weightlessness is very tough on the human body, both because our vestibular systems are completely not adapted, but also because our musculature and all the rest of our physiology are so terribly impacted by this. So we can have a long talk about the physiological consequences. I think we are at a very important stage in our history as a species, just in terms of the number of people that are here and the resources that are available. We have had an incredible luxurious existence in part because of fossil energy. We have been harvesting fossil energy for over 150 years. That is oil and coal and natural gas. And it's having consequences in terms of this carbon we're liberating into the atmosphere. We need to come to terms with this, and we need to do it rather quickly. Now, there are still people that are rebelling against this concept. Are you familiar with the 5 stages of grief? Do you guys know this idea? Raise your hand. The 5 stages of grief. So some of you know about it. This says that whenever you're in a situation that is terribly difficult and really unacceptable, your friend or your family member dies, or your boyfriend or girlfriend leaves you, something horrible happens. You go through 5 stages. First, there's disbelief, then there's anger, then there's sadness, then there's bargaining, and then there's acceptance. And you go round and round through these different stages. Climate change is a bit like that, right? We're angry, we're sad, we don't believe it, we bargain, and we accept it. And we go round and round. But you can't accept something really horrible happening unless you have an alternative plan. So what I'm presenting with the Omega Project is an idea that there may be an alternative to utilize the oceans in ways that are more ecologically sound. The real question is, what's the holding capacity for people on the Earth? If you look at an ecosystem, you could say, what's the holding capacity for any member of that ecosystem? And the numbers don't turn out to be very pleasant. The holding capacity of the Earth is probably, for people, depending on their lifestyle, it's probably not much more than 3 billion people, which is to say we're already way past the holding capacity for the Earth. So the idea that we're going to build things in space, that we're going to put millions of people that we can't no longer accommodate on Earth, to me is beyond my imagination in terms of doing it logistically and practically. The concept of finding planets and around other stars that are inhabitable, they're too far away. Forget it. Never going to happen. So I appreciate what you're saying, and I certainly, having worked for NASA for so long, you know, my colleagues would beat me up if I were to tell you that this is not a good idea. I mean, I think what NASA's doing is fantastic in terms of expanding our worldview, our universe view. Remember, the NASA budget is less than half of 1% of the federal budget. The NASA budget was used up in the Afghan war in 61 days. So, you know, it's just a tiny fraction of what the United States invests its money in. Sad to say, right? But what I think we need to do as a species is get very serious about solutions and real space solutions. The Omega is just one possibility, and the FARM project is meant to be another possibility. What both represent are closed-loop systems. We have to start building ecosystems of technology. Right. That's the concept, the future systems. Any other questions?
Şu arkada bir yer önce kalktı.
Thank you for the presentation. My question is about the return of resource investment in case of Omega project. To be able to create an Omega site, you need to use some resources to start with.
So you're talking about ROI, return on investment, or you're talking about...
I'm talking about ROI not in the sense of funds, but in the sense of CO2 emissions that you need to do to be able to create an Omega site.
Yeah, so in principle, the algae represent a really good CO2 sink because they're turning CO2 into biomass. If you burn them, then you're putting that biomass back into the atmosphere, but you're doing it in a short loop cycle. You can also turn them into biochar or some other kind of stable carbon that you could bury again. The return on investment in terms of the concept, I think, is really the reason I like talking to young students, high school students, about this project. Because the next generation is going to see a change in our society that is really quite challenging. You know, we already kind of see this because what happened in Syria was partly a consequence of the drought, a 10-year drought. And people were immigrating because of the political upheaval. But that kind of immigration is going to happen as climate change becomes more and more pressing, as it starts changing the way our farming is going on. And what I'm trying to present to you is that our species is been so successful because of our ingenuity. Our ingenuity has been focused to a large degree as this hunters and gatherers fighting off other people, and maintaining boundaries and keeping somehow our identity within our in-groups. But we really, really have to start focusing on the water, food, and energy nexus and how we're going to make that system sustainable. That is, long-term sustainable systems. And I think the first step is going to be realizing that the water, food, energy nexus, the water, food, and energy are not separate. You can't get water without using energy. You can't make energy without using water. And you can't grow food without water. And you can't harvest and process and distribute the food without energy. The three things, water, food, energy, are so intimate, we really have to start focusing on this. And the next generation of scientists coming out are going to be the key scientists and engineers and humanists and artists and all the people that are necessary to deal with all three of those problems that I'm now confronting, the location, location, location problems, not the least of which is the social attitudes that need to be engineered in order for people for people to accept this change in the way we do things. Because what I'm observing with all the people that I'm meeting is that what people want is for everything to stay the same and get better. And this isn't going to happen. So we need to start making things happen correctly. There was one other question. Do we have time?
Last question. Go ahead. You raise your hand.
What is the greatest challenge ahead? What is the greatest challenge ahead of farming project to become a reality, and what's your plan for it?
So the greatest challenge for the Omega project to come?
The other one.
Oh, the farm project. Yeah, so the farm project arose when I was in Denmark in spring, and I was talking to the Danes about the Omega system, and they said, oh, but we don't have a problem with our wastewater. We already process our wastewater. And I realized when I was visiting people in Kalundborg Symbiosis, I was talking to them about their symbiotic idea about industrial symbiosis. I realized that in Denmark there are 5 million Danes, there are 30 million pigs. And those pigs are living in big houses, and in the wintertime they're all kept warm, and they have a huge problem with their manure and their urine. It's huge. And they put it on fields, and it has to overwinter, and it was a huge problem. And so I thought that the pig problem can be addressed using the same concepts as the Omega project. Since expanded that, when I was in China, the Chinese right now are producing 400 million tons of waste manure every year. To put that in perspective, if the average Chinese person weighs 80 kilograms, that's 3 times the weight of the whole population of China every year produced in manure.
That's a lot of shit.
It's huge, a lot of shit. And it's not really utilized. And building a closed loop system will be great. So I think the next step in this project is to build a demonstration to show how we can make this work. The anaerobic digesters, we know how to do that. We know how to grow algae. We know how to extract nutrients from the manure. We know how to do all the parts of it. But putting it together and showing how it works, and it bootstraps each part and becomes profitable because you're now producing more products from this waste material, including feed for the animals, which is the #1 expense on any farm. I think this is the next step, building a demonstration. And part of the reason I'm here was because Berat and I have been talking about, could we do this in Turkey? Where would it be and how could we build it? Because once somebody builds it, the rest of the world will copy very quickly. And once we start building closed loop systems, then everybody will start building closed loop systems. And it has to be economically viable. It has to be bottom line, can you make money doing it? That's why I called it the economic project, because economics has to do with wealth, but eco has to do with ecology, and nomics has to do with the laws of ecology. Anyway, that's a good question. Thank you. Do we have time for one more
Jonathan,
question?
I think we're going to close the session in the interest of time. I'm going to allow people to
Yeah,
approach.
I'm happy to answer questions.
Arkadaşlar vakit darlığından dolayı kapatalım ama eğer soru sormak isterseniz 1-2 dakika daha burada olacak. Hepinize geldiğiniz için çok teşekkür ederiz. Boğaziçi Lecture serisi okulun YouTube kanalından yayınlanıyor. Eğer gelemeyen, katılamayan arkadaşlarınız varsa onlara izletebilirsiniz. Onun dışında Jonathan'ın 2 tane TED konuşması var. Özellikle genç arkadaşlar için çok tavsiye ederim. Yine gelemeyen arkadaşlarınıza tavsiye edebilirsiniz. Son olarak Jonathan'a tekrar teşekkür ederim katıldığı için. Size de geldiğiniz için çok teşekkür ederim.